I hope my both audio and video are working fine, right? You're able to see me and you're able to, I have not shared the PPTs, but you're able to see me, right? Is that happening? So you're able to see and hear me? Yeah, perfect. Okay, so let me share my desktop and we will start. We'll not waste the session since I have planned today's sessions to be a smaller duration sessions, technically smaller in the sense we will focus on more discussion but not more on the topics, right? So I've just shared you my PPTs which we worked on the last session where we just had the introduction to the graph, right, and the representation. So in the last session, I think we started with this. Let me activate the chart board also for a minute so that I can see the chart when I'm teaching. Right? Okay. 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 So that should be fine. Okay. Now I hope everything is perfectly visible. Okay. Okay. Perfect. Okay, so there is one question regarding there are two things. Let me first clear before I start the session. So we are continuing the last session topic where we left out with the graph traversals. So we'll first continue with the breadth first, then depth first. Okay, after that we will we'll work on something called as minimal spanning tree. Before that, I'll give you a small introduction to the greedy approach, but we'll not work on any greedy algorithm. We will work on a greedy algorithm in the next session that is called as half-man code. Okay, so let's focus on what we are going to have the discussion. So we'll have the discussion on first graph traversals, and then we will slowly move on to the rest of it. Okay, and two most important, since my machine webcam somehow did not respond, I'm using an alternate webcam, so my view would be little diverse from the camera. So I will be not looking at the camera since I'm looking at another system. Okay, so please adjust for this. And apart from that, there are two lectures that I'll do re-recording because as there is an issue with the webcam integration. So and one has been partially recorded. So two, that is contact session 10 and contact session 11, both will be re-recorded. Okay. So very good morning and welcome to the continuation session on session number 11 regarding the graph traversals, right? So first of all, in the last session, if I am not wrong, I have told you that there are two types of graphs, right? I told you there are three types technically of the graph traversals, out of which we'll be focusing on two, that is breadth first search and the next one is depth first. At this time, I told you that time complexity is going to be order of V plus E. Why does order of V plus E is? Since I am traveling all the vertices and I am traveling all the edges. So basically, technically, I am visiting. So I am trying to visit the whole graph, right? So that's why it is order of V plus E. That's also we discussed. Now, first of all, to implement a tree traversal, I should remember which data structure I am going to use. So I have mentioned to you that I'm going to use two data structures, that is stacks and queues, right? Now we'll focus first on breadth first search. Once you understand, then I'll go for depth first search. I assume that you are comfortable with the terminology of a graph. A graph is represented with a set of vertices and set of edges. So that's why whenever you go, people write G is G of V comma E, which means graph. A graph is none other than representation of set of vertices and set of edges. Now let's see the examples that you see here actually represent you the tree, correct? These both are representing tree. But in the last session, we have discussed a tree is none other than a subset of a graph, right? And if I have to talk regarding tree, can I say tree is a acyclic graph? Can I use the word tree to be a acyclic graph? So if you respond to that, it will be really a very interactive session. So you just let me know whether tree is a acyclic graph or not. A tree, can I call it as a cyclic graph or should I say it as an acyclic graph? It's acyclic. Okay, now I'll introduce a small word called acyclic and a word called cyclic. What is cyclic? In a graph, except the outermost boundary, if you are traveling in any other place, if you find cycles forming, then you can say it as a cyclic graph. And a cyclic graph is a graph that just doesn't form any cycles. For example, a tree can be simply called an acyclic graph, right? So that's what were these two terms about. So we will first try to understand, this is all the theory behind which we discussed. First we'll try to understand. Okay, sorry. I hope my audio is now audible, since I heard someone said there is no voice proper, right? Okay. So first we'll try to understand breadth first search or breadth first tree travel search. Okay, so here it is the breadth first search. We can use the word properly search. The reason is I'm going to visit all the vertices. So do you want me to call the vertices or do you want me to call the word nodes? Which one do you prefer? Acyclic is a graph. Okay, you want me to call nodes? Okay, perfectly. Okay, so acyclic is a graph which visits all the nodes or vertices and it is not still forming a cycle. I can say it as a acyclic. For example, in a tree, do the start node and the end nodes remain the same? No. So that's why a tree can be called as acyclic. Okay, right? Got it. Okay, now let's first try to understand if I am going to implement a breadth first search tree travels or graph traverser. See, a graph traverser, how will it look like? Okay. And the data structure that I'm going to use is stacks or queues because BFS is already covered, but since for continuation purpose, I'm recovering BFS. So which data structure would you prefer when I'm implementing a breadth first search graph traverser? Which one would be stacks or queue? As you have answered, it is queue. Perfect. So let's say, now let's assume, I hope you are able to see a proper graph, right? Okay. So the property of a queue is first in, first out. Okay, so I do DQ, I do NQ. When an element exists, I can if I'm adding an element into the queue, I say it is NQ. When I'm deleting element, I say DQ. Okay. See, let's try to understand the basic fundamentals of breadth first search. Okay. First, let's say you are starting from root. Okay. When you are starting from root, I hope we have already learned about breadth first traverser in its trees, right? Shruti, actually I am not on mute, Shruti, because for your sake I had to once cross. Yeah, okay, so do you getting echo anymore now? Okay, fine, so okay, that's great, because I'm using multi-audio system since people have requested. Okay. Okay, let's look at this tree. First of all, sorry, look at this graph. When you are looking at this graph, you are saying that this graph is not necessarily to be a cyclic graph because the start and end of these graphs are not the same, right? After B, I am not directly connecting to A or so, right? So that's fine. Now next question, is it directed graph? No, it's not directed because it's not pointing any arrows towards others. Perfectly. Is it a weighted graph? No, it's not weighted graph because there are no weights on the edges. Perfectly everything. But do we have to implement the same thing for tree traverser? For tree traverser, weights doesn't play important role. But when do these weights play important role? If you are talking about finding a shortest path, then weights play important role. That is also part of today's syllabus. At that time, I'll make it pretty clear. Okay. Now, no confusions about how this graph looks. So every graph should be always pointed out with a start node. Here I am assuming my start node to be A. Perfect. Now, when I am starting from A node, let's see, how can I travel in a breadth first? For easier understanding, remember the root of a tree. How, if you are traveling a BFS, Rahul, let's not get into the picture of the in order, pre-order, and post-order for a minute. Okay, you have thought it in correct way, but just for a minute, just Do not worry about pre or in and post order, because that will again confuse the other audience, right? So let's say you are at a root. Now, when a breadth first search, let's say it's a binary search. How many chains it will have? It has got two chains, right and left. Now I can travel left or right. Perfect. Okay, done. I am at level 2. Now, if I am not visiting my if I am not visiting my cousin or my sibling, the sibling, correct word should be sibling, I cannot say it is a birth first search. In breadth first travel, we said all the nodes in each level should be visited. So at level 1 we have got 0 node, at level 2 we have got 2 nodes, right? These 2 nodes also to be visited. After that only we go to level 3, then level 4, level 5, so on. If you can recollect, it is fine. If not, work. Now take A as the root. In this following graph, can you see A as a root? Because I am saying A, can I say A is my start point? Now just assume that what are the chains of A? If I would ask you this question directly, what are the chains of the A? Assume in this graph, what is the chain? Yes, ID. Perfect. No need. So I hope now it is very clear for you. That's how we are doing. Right? So in this session, let's have a look at this. So what happens is you are at A, okay, you are at A, you can either travel to I, you can either travel to B, okay, but after completion of I and B travel only, you can go to next visit. For example, how many people like traveling? Because the real life scenarios actually makes you much easier for understanding. Everyone loves to travel, right? Now I'll just talk about you. Let's assume that you are at Hyderabad. Okay, do you want me to take example of Hyderabad or any other place? I'm sorry, because I am sitting at Hyderabad. I just told Hyderabad. Any place is fine. Perfect. Okay, Delhi. Okay, cool. Delhi is also fine. Okay. Sham, Bangalore, I have not been visited. So Bombay, we'll take it up. Okay, for example, we'll take it up as Bombay. Okay, because none of the options, right? Okay. In Bombay, let's take a simple example, or Mumbai. Yeah. So I am standing at VT. Let's take I am standing at Victoria Terminal, or now it is renamed as Chhatrapati Shivaji Terminal, CTA. Okay. Now I am standing. Now let's say that's my route node. From there, can I travel to Dadar? I can travel to Churchgate. I can travel to Marine Drive. Let's take this as my example. Let's take this as example. Now I decided I will first visit Churchgate and then I am going to Marine Drive. So which would you see my travel is happening? How I am traveling? Can anyone guess a pattern there? Once you get a pattern, I'll just try to make you help. Okay, so for easier understanding, the VT and Churchgate are adjacent. So you can say they are south of Mumbai and Dadar is towards the north of these things. Yeah. Okay, Dadar is north of these things. Okay. So once I am at VT, my first preference is to finish Churchgate. Then I am thinking to go to Marine Drive. These two things I have decided. Now, if I am doing this, what it means is after reaching VT, I am just trying to explore its adjacent, right? And this is one way of travel. Other way could be something. Churchgate to Dadar, from Dadar to Navi Mumbai, and so on. And I am traveling. This is a linear. If you see, if I am taking one path and going all the way till its end, that can be simply said as depth first search. Okay. No, short will not bring here. Shortest will not bring for an instant. That as we will do. And if we are trying to travel in such a way that I go to one point and try to explore in and around it, then I will call it as a breadth first search. You understood that, or do you want me to repeat? For example, let's say you have come to Hyderabad for your official work at High Tech City. Let's take this as an example. Then you have come to visit Hyderabad on an official trip, and you have come on an official trip and you were located at High Tech City. Now, IKEA, I think most of the people would have taken this advertisement of IKEA, right? No. See, inside city, one small location, Prasanna. It makes the example much easier. That's all. Okay. So let's take, there is a small place called High Tech City in Hyderabad, where IKEA is close by. Now when you reach high-tech city, after your office hours, you go to IKEA. This example I can say it as a birth fair because you are exploring areas that are close to a particular point. It's a particular to a point, okay? For example, if you take this people who are traveling on motorcycles from one point to other point, let's say someone say I would like to, okay, let's look at annotator. Sorry, this pencil I'm not using, that's why this, okay, I'll draw for you, 1 second. Okay, I'll just draw for you. Once you understand, we'll go. Let's say someone is traveling from Kanyakumari all the way to Ladakh. His journey is only to travel. Okay, his agenda is only to travel, not to explore. If he is traveling in a particular order, let's say if Kanyakumari, you might have other routes also, like some other routes can also be there, which will lead to different places. Let's assume this could be a scenario. For your understanding, I'm just taking this example as a scenario. Don't worry. Okay. Now let's say this is the South India, that is especially a Kanyakumari here, right? Let's say this is Kanyakumari. He has to go to Ladakh. Here, Ladakh is somewhere at this moment. What will be his path? I hope he will be traveling like this, right? This is the one way. Is this a travel way of someone who is planning to travel from Kanyakumari all the way to Ladakh? So if you see, he is not even bothering about what are the places adjacent to the other nodes. These places is not at all bothering, right? So now if you see clearly what it is happening is, now what it is happening is, if you are traveling in one particular direction, this can be said simply as depth first search. Okay, you understood the depth first search. And if you are exploring, if it's an explorer, he has gone to Kanyakumari, he would like to visit all the places in and around it. So he has got to some other point, he would like to explore all the places in and around it. Right? If he is traveling in level by level, then we call it as a breadth first search. Have you understood that? So if you are traveling in a graph level by level, I can say it is a breadth first search. And if you are traveling in a particular direction till you reach to a dead point, you call it as a breadth first. So right, now let's try to finish this example. And I'm sorry, I'm not using any teaching aids here. That's why my diagrams might be a little bad, but I'm trying to work at the best. Okay, right. So let's try to, and our start point is A. Now my start point is here from where I'm going to start. Now once I have decided that my data structure I'm going to use is a first in, first out. Perfectly, that sounds good, right? That is Q. Now what is the node that I have visited? Can anyone quickly say? If I say something as start node, it means from there it is my start point. Right, so A is my start node. So first point is A is pushed into. See, I'm sorry if I'm using the word push and pop. Please reiterate themselves to DQ and NQN. So first step is I'm NQing my A into the Q. Done. I did the NQ. Now, which will be first element I have to delete if the deletion operation is to be done, or what will be the DQ element if at all I have to do? You just answer which will be the DQ element. A itself. Now we understand perfectly good. Now what are the adjacent nodes of A? I think we remember what do you mean by adjacent. The nodes that are connected to each other, we call it as adjacent. Here there are two adjacent nodes, that is B, I. Someone can say, can I say I and B? Most welcome. You can say either B, I or I and B. Any order is fine. Only the difference is your order of visit. Someone says A, B, I. Someone's answer will be A, I, B. But still I and B are at the same level. It will not give any effect because we are not working on the shorter distance. You understood the difference? Why it will not affect? But if it is a distance, shorter distance finding algorithm, then that is a different story. That's where we will be talking about minimal spanning tree or single pair shortest path algorithm or pair shortest path algorithm. You understood? Here we are not worrying about the distances. What we are worrying whether I have visited or not. It's as simple as if you go for a tour and once you come back, what will be your friend's question here? What questions would your friends have? Have you visited this monument? Have you visited this place? Have you had food at this particular hotel? Yes, they will not ask you in what direction. Okay, route is always the first node that is to be enmarked by the question. If I am giving a question paper, I give A as a star. If, for example, I have forgot to give here you anything to the marking point, since it's undirected, you will have a freedom that you can take anything. Okay, if I have forgot, you can take anything, but it should be undirected. If it is directed, you will be able to identify which is the root node. Okay, assume that this is a directed, assuming from A all you have outbound nodes. A has no incoming vertices or incoming edge. Which one will you consider as? In those cases, take the one which has no incoming vertices. Got it? So let's say this is all directed and let's say this you have all directions. You have to take the node which is not having any incoming vertices. Got it? So you understood how to choose. Technically I will be giving. Even this all cases did not work. If someone is saying the order of the nodes are A, B, C, D something, then you will take the A as your start node. Got it? Technically either start node will be mentioned. If it is a directed graph, the graph with no incoming edge will be taken. Even in spite if all the cases are missing and they have written following vertices, following nodes, the graph contains A, B, C, D, E, F, then you should choose A as your start point. Now you understood which one to choose as your start point? I hope yes. If you say yes, then we will go. Okay, let me go to the, yeah, okay, let me go. Now I have chosen my DQ should always happen with A, but if I do DQ of A, what will happen is, without having the information of their adjacent, I do not prefer to do a DQ. But I mark A as visited. Okay, A is a visited. Now what I did, the moment I say visited is, I am actually trying to take out from this queue and trying to push to another queue called visit queue. So if you can maintain visit. Now I have to mark, I have to also enqueue their adjacents. What are the adjacents that I will be enqueuing? B, okay, and I. Got it? So this order is the student's choice. Someone says, Prasanna, I would like to do I and B. Yes, you can do. Okay, got it? Now you can do any. So I did B and I is the order. This A, what is the A I am marking is, I am just trying to note what are its parents. If you have not marked, do not worry, but for easier understanding, I read I and B because from the A's node. Got it? Why A is marked? No. Now what would be the next step? Can anyone say? So now if you see A is visited, what are the next two visits we have done in our places? The place B and place I is been visited. Now next. Now my visit is done. Now if you see, if you look like tree, the root A has got two childs, that is child I and child B. Did I visit them? As my visit of A, after A, IB is done. So you can say yes or no. If the visit of I and B is done, no. Okay, yeah. Okay, person I understand because I have to DQ it. Great. But technically, at least I knew that I am going to visit B and I at least. Got it? Now B will be my visited. Okay, because A is done. Now all children are done. So A I can print out saying A is visited. Now I will consider, because next DQ element is B. So B, I will have to identify B's adjacency. What are B adjacent list? One is A, one is F. Right? The adjacency list of B is A and F. Both A and F power are present now. But I will not consider A because A is already been in the print of visited list. It's already there in the visited list. So I can't revisit it because I said I visited. Only I am trying to explore what are to visit. So yes, definitely I can only enqueue F into my queue. Right? Got it? F into my queue. Now after this, do I work on F or do I work on I? Which one will I work? Will I work on I or will I work on F? Why I? Because I am working on FIFO is my data structure. So I can't work on F. Definitely it will make sure I work. Now you see, after A, all the visits have happened at that level, that is I and B. Now got it? So now I is, so I have decided A, we have said nothing. Okay. So we are working on I now. So I's adjacency is E and A and F, right? See, it's A. So if I's adjacency list is A, E and F. So which one will I choose and push into the queue? Will I push A or will I push B or will I push A, will I push F or will I push E? E, you are correct. Why? Because F is already in the queue. A is already visited, so I don't need to work on existing and visited. So E is the only unvisited. So I have marked it. So right now E will be enqueued. Okay. So now what is the next element that I'm going to dequeue? It will be F. Right. So you can see F. Now once I have decided to dequeue F, so this all we just did fast. Okay. I have decided to dequeue F. I have to find its adjacents. What are its adjacents? B and G. I'll not use B because B is in the already visited. Yeah, B and G is correct. B is already visited, so I will be enqueuing only G. Right? See here. I'll be enqueuing only the G. Right? Okay, got it. Now, in next I'll be working on E. Now E, will I be able to have any adjacent vertices? Yes, E has adjacent vertices like I and F, but E has no new unvisited. So E will, yeah, E's adjacents all are visited, so nothing to worry with E. So E will be just simply DQ. Now G, only G, it's before I DQ, I have to identify its vertices, that is C and E I just finished here. So next is about G. For G, it is C and B and anything else, sorry, it's C, H and F, not D, Mrudula, it's not D, it's F. I think it's typo error, right? Okay, so technically F I will be not pushing, I will be pushing only, I'll be queuing only C and H, right? Now what is the order of IDQ? IDQ C, okay, so when I'm dequeuing C, then I have to also make sure that D is being pushed in, right? So HD, then H will be DQ'd and nothing for H, okay? So for D also we don't have anything, so now, so we have finally our printed list. Now you understood that, how we did? Sorry, actually what happens is, that's what I told you. In programmatic, when you are working programmatically, what happens is, in program you will also have another list called simply, called as visited. So if you have element in that particular list, you doesn't need to enqueue into the queue. Got it? Okay. Now someone wanted me to write the list in the order we printed. So let me write. So first visit was done with A, CQ, A. Okay. Now, what was the next element that we visited? Was it B or I? We visited B. Okay, C. And then next visited element was I. Okay. Now you help me out. The easier thing I did. After did I printed E or did I printed F? Yeah, correct. That's F. After F, it was E. Right? After F, it was E. Now after F, it was E or G. So it's E. Why? Because E was the child. Okay. Why? Because E was the child of I. So that's why E then F. You got it? So after F, it is G. Then it is C. Then it is H. And then D. Now, this is the order in which I have done. Now let me interchange something. Let's see whether my answer is correct. A, B, I, okay, A, I, B, E, okay, then F, comma, then G, comma, C, comma, H, comma, D. Is this a correct order? Will you see the beneath one? Do you find it's a correct order? Yeah. So you understood. So all users cannot give a unique solution. Got it? So what I'm saying is only consideration is if you are able to travel all the levels, then it is a breadth first. So time complexity, I told it's order of B plus E because you are going to visit all the nodes and you are going to use all possible vertices. Right, great. Now we will work on something simply called as DFS. Okay. Here I'll be taking Divya, for which you are asking the answer, Divya. Okay, you wanted me to type the answer, right? Okay, just give me a second. I will do that for you. So you, in the previous case, I just typed your answer as A, I, B. Okay, A, I, B, comma, then E, then F, then I took G, then I took C, sorry, then I took C, then I took H, and then I took the D. Is the last node is the D? Yeah, it's the, okay. No, I just typed right now here. Now I think you have seen the answer that I just sent in the chat board, that is A, I, B, E, F, G, C, H, and D. Right? That is the other answer. Someone else also can rework on the G, H, C, D order. Right? So that there will be three possible answers. So that's why we cannot say there is always unique. Right? Got it? So someone can say I can have G, H, C, D. See, breadth first is Vishwajit. Why? Because let's take G node. Let's just work on the G node. Okay, for your example, I'll take. So let's forget about all this. Just remember you have got G. What is the chains of G node? What is the chain of G node? Vishwajit, you are going to answer me up. Yeah, chain nodes of chain nodes. Yeah, just forget. You don't assume this. You have anything. Okay, just work on this graph. Now say what are the chain nodes of G? It's C and H, correct. If you see the output you are printing after G, either you are printing H or you are printing C, right? Is this one possible case? The other case is either G, then C, then H. Are these two valid or invalid? First you say, are these valid or invalid? Now F, follow me, for a minute I said, forget, you don't assume that you don't have a tree here or you don't have a graph. Just for an instant I said. Okay, that you're not working on this, you assume you started at G, for instance. Okay. Now what happens is, now when you are at G, what happens is after visiting G, I am visiting the directly connected edges, and after finishing these two visits only I am going to next. Understood? That's why. For G's direction connection is C and H. D is not directly connected. To travel to D, I have to travel to C and then D, right? Got it. So after G, I am finishing all the nodes that are connected and then I am going to the next. Got it? That's why it is called as breadth first. Now you understand? Got it. That's why it is called as BFS. If you are saying no, I visit G, then C, then D, then you are saying I am traveling in a particular path. That's why I can only come back till I go to dead end. That is breadth first. That is depth first. Okay, let's work on the depth first search. Okay. Now, here I would be trying to do it much easier way so that you understand. Anything here, Pawan, you are correct. Any element you can. For your case, I'll take this as example. So in this case, can you say A can, okay, before I go to DFS, I have few questions. Do I mark here the start node? Did I mark any element as my start? Is my question. See, forget about the task. Do not focus at this portion. It's a directed graph. Okay. Yeah, it's a direct. Out. Okay, sorry, slow. Okay. Okay, sorry. So you see, for example, the following graph, if you see, what happens is it's a directed graph. Does the start point is marked or not? Can anyone say is the start point marked? No. In this case, how to choose the start? But if you take A as root node, just can anyone assume A to be a root node for instance? Can anyone say A is a root node? For instance, if the people who are saying yes, what is the concept of root here? Root is the node from where there is always outbounded edges. There are no incoming edges, right? That is what you see. Now in your A, if you see A has an incoming edge from H, A has an incoming edge from H or no? Now, which is the node in this case? Technically, we'll give. If at all you see the node D, D is the only node from where there are all the edges going out. So that you will have to choose D as your root node. Got it? How to choose? G, if you choose, G has an incoming from E. G has an incoming edge from E. D has an incoming, D also has an incoming edge from G. You got it? So in this kind of cases, what we can do is you can choose anything. Okay, but technically, if at all there is no incoming edge from G to D, we would prefer D. Got it? So you have this, now you understand? Now freely you can choose any node as your root node. That I am going to say. I'm sorry, I forgot to say that. Instead of that, I told you that outbound zone. Got it? So D, we are choosing it here. Okay, so now let's say I have got to work on the breadth, the depth first search. Okay, and the data structure I'm going to use is a stack. By looking, you're able to make this a stack. So this is a stack. This one is stack. Okay, okay. If I take A, yes, definitely, because I'll just work with A to B. And I do not have any other paths. From B I have just N. So I will take such a node that where I have mostly I am able to travel. Right? So multi conditions we put here. Okay. So we are working on now depth first search. Just let me finish the depth first. BFS will use Q and DFS will use a stack. Absolutely correct. So you are going to, if you are using stack data structure, your outcome is always BFS. If you are using Q data structure, it is always BFS. Okay? Okay. Now the start node is D. I have mentioned here D to be our start node. The moment I say, yeah, it's a directed graph. To make your problem little easier, we decided to use a directed graph. Okay? So let's say I have made D as my start vertices. What it means? I have visited D. So I push D into my stack. Okay. What is the funda of the stack? First in, first out, or last in, first out? When you're using it, last in, first out. Okay. Now D. What are the adjacencies of D now? Can anyone say what are the adjacency lists of D? Say the adjacent list from D, E and C. Okay. Now I push them. So when the moment I push them, are they B sitting on the top of D or they're sitting at the bottom of D? They're top. Okay. Now I'll show how it works. So D is the visited node, but D is just visited node, and its adjacency list, the adjacencies are C and as well as E. You got it? So let's work on 1 minute. 1 second. I just moved little fast. Okay. C. Okay. First I have decided C. Now then if you see E. These are the two. First, just for an instant, did you understand what are its adjacent? It is C. Okay, there is a question. Why not F? You can choose. Okay, there is a very good question. When I talk about the adjacency of D, the adjacency list of D is C, F, E, right? Or all the three are adjacency lists, or no? First, answer me that question. C, E, F. No, C, E, F. All three are correct. They are adjacent because D is connected to C, D is connected to E, D is connected to F. You can say C, F, D. All are connected, right? Now, that's why I can say. Now, you have to choose any one. Which one would you choose? See, in my case, I have chosen C. Okay? If you say E, our answer will be different. For easier understanding, we'll take C. Now, I have chosen C. Okay, I have reached the C vertices. See, student has a freedom to choose E or F. That we will do at the end. 1 second, right? For instance, I am choosing. Can I travel to C further? So after C, what are the C's adjacency lists? Same way, what are C's adjacency? There are no adjacency. Assume that when you are having no adjacency list, it means you have reached a dead point. When you are traveling, you have reached a dead point. For example, let's take a simple example. Someone wanted to start traveling from Hyderabad to Kanyakumari and then from Kanyakumari to Kochi, from there to Goa. Okay, let's say this is the way. I hope people remember the V shape. People remember V shapes, right? Okay. For instance, so I have started from Hyderabad. What is my next destination? What is my next destination? I told I wanted to visit 4 places. From Hyderabad to Kanyakumari, Kanyakumari to Kochi, Kochi to Goa. This is what I have decided. Actually, Hyderabad to Goa is the fastest route, but I decided this is my travel. Now, after reaching Kanyakumari, what I am doing, if I still travel, where will I go? Actually, I will go into the sea, definitely. No, if I travel further without reaching Kochi, if I travel, I am getting into this. So, is it the dead end of the landmark? Can you say Kanyakumari is my dead end of the landmark from where I am reverting back? Right? I am reversing back my travel. Now, so after C, it means I have reached to the Kanyakumari. I can't travel further. I have to revert. So before I do revert, what I should do is I have to pop out C. So I am popping it out C. Popping is done. Now D is visited node. C is also visited. So you see, D, C are visited. So I have visited Hyderabad. I have visited also the Kanyakumari. Now I have to go to Kochi. So now, if you see, what is the top element in your stack? What is your top element in your stack? No, C is popped out here. So D is the top element. What are the D vertices now? Say adjacent vertices. कौन से D के adjacent vertices? Yeah, E, F and C. You are correct. Again, we have come to the starting point. E, F and C. Now, the moment I came to E, F and C, what happens is, C is already visited, so I am not going to visit again, so I have to visit E again. So which one will you choose? Is, let's take, we have decided to visit E. So I have visited E. Now, after E, can I go further? Can I go to G? Or what is the adjacency of G? Yes, so let me go to its adjacency. So adjacency G is visited. After G, what all can I visit? I can visit H or I can visit D. But D is already visited, so I have to visit H. Now you got visited H. Now after H, it is either A or B. Because A or B I can choose. So let's say I have chosen to visit A. Okay, I have chosen to visit A. After A, is a deadline? Is it a dead end? Is A dead end? No. So I can go to B. Now, after reaching B, can I still travel further? If you see now B is my dead end. Can I travel further? No. So I start popping it out. So B I have popped it out. Can I travel anything to A? No, because A is also popped out. H popped out. G popped out. E popped out. Now I go to D because D has only unvisited. See, new. Whatever. If you have something at H as unvisited, you will work on it. Since you doesn't have any other thing, you will come all the way till H. Till D. After coming to D, you have unvisited, which is F. Push into the stack. Again, F has become dead end. So pop out. And now D again pop out because D has no more unvisited vertices, so pop out. Finally, once your stack became empty, what is that? You have visited all the nodes in the order of B, C, E, G, H, A, B, F. Now it's done. This is the way how your depth first search works. Now I have a question for you. Okay, I'll just go back to the initial diagram. Okay, for instance. Okay. Now just say me. Let's work in a different way in the same example. Okay. If you have chosen D till this here, okay. Now instead of C, can I choose F? Can I choose F or no? Instead of C, can I choose F? If I choose F, your order is instead of D, C, it becomes D, comma F. Okay? Okay. After F, My next element choice will be C, right? So what will happen? D, F, I will go to C. Is this a valid method which I can do? Can I do? First I visited D, then I said D's adjacencies F. After F I moved to C. Yes. Now can I still travel further anything after C? No. I'll just simply pop out C. I'm striking it off here. I'm striking it. Okay. Then again F. Can I travel F2 further? No. I'll pop out. Right. So finally I have got D. Again after D I'll be going to E. Right? So got it. Now how can you do this? So there are different solutions you might get, but remember that you're following a clear way in which you want it to do. So if this is understood, let me check with answer. D, E, correct, then G, then H, then A, then B, then F, and then C, perfect. Even someone can also give this answer again. Because if your answer is correct, someone also can give you this answer. B, E, G, H, A, B, C, and F. That's all. So Pawan, there are multi answers. That's what I'm trying to say. In my case, my answer has been this one. B, C, E. Got it? This is my answer in my case. That's B, C, E, G, H, B, F. Okay, if you pick B as root, okay, there's a very good question from Pawan. Pawan says, let's say, assume B to be picked as a root. So you will not have any output because B is not at all traveling. So just your answer will be B. No, I just decided, okay, we have a very good question. So once you go here, let's look at the graph. Till this graph, it's clear, or you have any questions? Yeah, why my answer F is, till this point, F was not visited. If you see, F was not visited. So once I come back to D, I realize that D has got one more adjacency node, so F. So that path is to be explored. So definitely that's the way how it is. So I hope most of the people in India would have gone to Goa. I hope most of the audience would have gone to Goa. Yes or no? Just answer the simple question. No, Rahul, so you'll go soon. If whoever has gone, either bachelor or if you have gone with friends or if you have gone with families, it's one of the best days. So can anyone just Google it, Goa's capital? Which no, you have a Goa Central, yeah. So Panaji. See, if you do the Google, Panaji is actually a center. You have North Goa, then you have South Goa. So one day you decide to travel south, the next day you have to come technically back to Panaji and then you have to travel to the North Goa. Similar concept we will be using in our breath person. So see, all the way I came till D. So I visited all South Goa, then I came back to Panaji because basically I'm staying at Panaji. Now, okay, I'm just giving a real life example. So let's say this happened with me in my life. So we went on my wife's birthday to Goa. So we were saying, we were at Panaji. Okay, I was at Panaji technically. Since we were traveling for the first time and I was still at the beach, but we decided not to stay at beach Goa. So I was traveling and I stayed at Panaji. First day we traveled all the way to South Goa. We enjoyed the South Goa scenic beauties and we came back. After coming back, suddenly I have got a call from my friends, have you visited all the beaches? I said yes. Then these people told North Goa. So and next day I traveled North Goa. So how is my trip? Can anyone say, will you say this as a breadth first search trip or depth first search trip? Absolutely correct. It's a BFS. It's not DFS. Why I'll say? Starting from Panaji, I have moved to South Goa, first location, second location, third location, all the way till Delhi. Then I came back if I have to travel on the same way, I have to come all the way back to Panaji and still go. That's why it is a DFS, not BFS. Got it? You got it? Why it is a DFS? If you are traveling, you can use two stacks. The second stack you can use technically to print the visited list, but there's no point. No, Pawan, you have a very good question. Still, if you come back in the same point, what it happens is your length, root becomes different. Now, for example, if you take something like Humpy, you will have actually BFS. No, I have next slide is there here. This is the answer. F is a part of the answer. Okay, just there was another slide. Okay, so let's take quickly a small break. 1 second. There is a art is B, E, then G, then H, then B, perfect, then A, then C, F. Yes, Anisha, your answer is correct here. Okay, so let's take a quick break, and we will take break for 5 to 10 minutes. A dead end, then it is DFS. In DFS, you will have the last node only to be in the dead end node. Correct, yes. See, you can use BFS and DFS depending upon the data. Sai, I don't know, yeah, we are currently correcting the midterm makeup papers. Okay, so technically you should be releasing this week. Yes, you can do. You can do BFS on directed cyclic graph. Yes, you can do it. Not an issue. DFS is a recursion function. Okay, Vishwajit, there is a question which is a little important. So you can carry the printout of the class PPT. Okay, in a spiral binded or proper stack. Yes, you are allowed here. You are allowed to carry it. Okay, so let's quickly go for the break and then we will catch up on it. Okay, so there are few questions. Let me just quickly. You can carry the textbooks and reference books, so there is no limit. So do not worry whether it is 2 books or 3 books, but as part of handouts, you can carry those books. Okay. Okay. Next question. So one important one: stacks and queues by definition have no check if element present. Only push, pop, NQ, DQ. Right. Absolutely correct. Okay. Pranav has this question: how do I do the check condition? That's why a check condition, we always, when we are implementing, we implement one more list where we will try to see if the element is in the list, then we will not push or NQ into the queue or stack. Got it? So Pranav, is my question clear? Now you understood the question. I'm trying to say that if at all the push pop in directly stack and queue is fine. It's for the story. To cross check, we'll also have something called as the list. In the list or in other array, the element is present. You doesn't push or NQ into this stack or queues. Right? Any other questions? Okay. Okay, great. So let us start the. Okay, I could not see. Okay, let us start the session. Okay. Again, same question. When is can we call DFS as cyclic? Yes, you can call DFS as cyclic, but the problem, Rahul, but the final output, what you get by the end is actually going to. Okay, let me record here. Sorry, I just forgot. Okay, yeah, recording has started. Okay. Okay, can we call DFS as cyclic? Yes, you can call DFS as cyclic, but the truth is by the time your output comes, the graphs will look like something like trees. So the word cyclic doesn't hold as a correct answer there, right? The correct answer hold is acyclic. DFS's outputs are always acyclic, DFS and DFS. Okay, why are you NQing and DQing? See, the reason for NQing and DQing is to ensure that all the level elements are visited. That's all. You NQ and you DQ to say that this element is visited and you are printing it out. Got it? And if it doesn't DQ, what will happen is you cannot ever visit the last element. So that's why you use NQ and DQ in your queues. For example, let's say someone has not said, okay, let's take this as it. Someone has said, do the following traversal on a particular graph, and the data structure that you are going to use is a stack. Then the only way that you can implement is depth first. If the data structure someone says you are only supposed to use Q, then the graph traversal will be BFS. Okay, so you don't need to worry too much on this. The data structure, whatever you use, the output will accordingly change. If you say stack, assume your output will be always a depth first. If you say Q, your output will be always breadth first. Okay, so let's quickly go to the next topic, that is the agenda, and an important and interesting topic in your in the session, right? So we will be working on something called as minimum spanning tree. Okay. Before I go with the word minimum spanning tree, first let me talk about the word spanning tree. Before spanning tree, let me talk about the trees. Are everyone comfortable with the tree topic? If at all a nodes are given and a tree is constructed, you will be able to identify which kind of tree. Yes, perfect. Now let's talk about, can I say tree is subset of graph? You agreed for it. Yes, you agreed that tree is always a subset of graph. Yes, okay, done. Now if all the nodes, if you did BFS or DFS, but any node got ignored, first answer these questions. Whether, okay. Please speak 2 minutes on complete and full binary tree. Who has asked this question? Okay, I just missed. I just missed the question, which I'll scroll down and I'll just again have the discussion here. Okay, just let me finish. Just give me 2 minutes to first understand the term spamming, and then we'll go. Okay. So you are clear with the trees. I'm not worrying whether you talked about breadth, you talk about a binary tree, singularity tree. You are comfort what is a tree. So that's enough. Now in the output of BFS and DFS, what was the output when you had a graph? You traveled the graph, either be BFS and DFS. What was the output you got? Can I say the output was something like a tree? Especially in DFS, especially in DFS, was your output was a tree? Can I say that example which we have taken, the output I have drawn was looking like tree? Do you want me to show once again? Let me give you a second. I'll show you first. Just 1 second. So just 1 second, so that BFS output for easier reference, I'm just once again reopening it. So I'll not enlarge it. The last output. Yeah. For easier reference, the output is looking like tree? Yeah. No, just looking. Sham, I'm just saying, is it looking like tree? Nodes are connected and so on. Is it looking? That's all. I'm not even going for the technicality. Just for easier understanding, I said, okay. Now, when you have seen this output, are all the nodes connected? Are all the nodes connected, or few nodes have got missed, or few vertices got missed? I'm not talking about the term edge. I'm just talking about the term nodes. Yes, all the nodes got connected. Now, in a graph, if you are able to give all the connections by eliminating some other edges, and still if the graph is connected, then those kind of graphs we call them as spanning trees. Spanning of all the nodes. If all the nodes are connected somehow in a graph, and by eliminating some more nodes, we can say that as a spanning tree. Okay, I'll just show you an example for a minute. Can you say this is a connected graph? Can you say this is a connected graph? Just say. Yes, this is connected. Perfect. To reach D from G, what are my paths? to reach D, what are my paths from G to D? From G to D, how can I go? Easiest path, G to D direct path, GED path, right or wrong? GHAFCD. There are multiple paths, yes or no? Multiple paths? Yes. Okay. There are multiple paths. The answer is yes. You say that you have got multiple. Now, if somehow I remove, let's assume there is no path, I have removed the path between G to E. G to E. Okay, let's say there is the direct path I have removed, or let's say I have removed path from D to E. Can I go from G to E? Okay, which path do you want me to remove? You want me to remove the path G to E or G to D? Sorry, D to E. Which part do you want me to remove? For instance, for a small example. Any path of my choice, so okay, D to E path I have removed, great. Now if I have to travel from D to E, I have no path, I just removed for instance. How will I go if there is no path from D to E, but from DE how will I go? Yes, D to G, G to E, yes, perfect. So if all the nodes are connected somehow, if the nodes are connected with one another, we can travel. If this functionality is given, if you can span all the nodes or vertices in a graph, then we call it as a spanning tree. Understood the concept? If you see, look at this, this is a graph. And some of you are removing certain edges and still all the graphs, all the nodes are connected and you are able to travel to one to other node, that it is called spanning. Spanning means visiting. Okay, you will be able to visit all the nodes in a graph, right? That is the term spanning means. Okay, okay. Now let's talk about the word minimal spanning. What is the word minimal spanning? See, if you are using the minimal edges to connect all the vertices in a graph such that the total cost of traveling all the vertices is very low, then we call that as a minimal spanning tree. You understood the spanning word for spanning tree, you understood? Shorter distance traversal is a different concept. So, Vishwajit, I am not going to use the word shortest, but here I am trying to say the smallest possible connection that I am trying to make between two vertices is the best example I can say. Okay, for your easier understanding, I will draw a small graph. Just hold on for a second. Okay, let's say I've got an A. Okay, A to B. Let's take this as some connection. I have got C. This is the connection. Now, this is a graph. Do you agree with this? This is a graph, right? Now, my questions are this. If you understood this, we'll have a very good discussion. A to B, B to C. Can I say this as a spanning tree? Spanning tree, sorry. First, let's say, can I call this new diagram as a spanning tree? Is this a graph? Okay, first this is graph. This G is graph, and this is spanning tree. Sorry, can I use this word? This is the graph A, and this graph I'm generating this spanning tree. Is it a spanning tree? Okay. One more example. A to C, A to B. Which one is the spanning here? Is this is also correct? This one is also a spanning tree? Yeah. Okay. Now we understood this. Now one more example. I'm just adding values. 2, this value is 3, and this value is 5. Sorry, my writing is bad because I'm using the pointer one, so just excuse me. Now here it is 2, here it is 5, okay. Here it is 3, here it is 2, okay. Okay. There are two spanning trees. The first spanning tree, what is the cost to reach C from A? From A, what is the cost? It is 7. Okay, great. In the second case, what is the cost? from A to, no, A to C, just A to C. A to C is 3, okay. And what is the total cost that is involved in the spanning tree 1, this one, what is the total cost? 2 plus 5 is 7. And what is the total cost involved here? 2 plus 3, 5. Which is the minimal according to you? Which graph is ideal for you to choose? Why? Because you are able to travel at a minimal cost. So if you have to travel from B to C using second graph, what is the total cost you are spending? From B to C, 5. Even if they are directly connected, still the cost remains the same. So if you are able to derive any from a graph these kind of trees, you call that as a spanning trees. And the minimal which you are able to derive, that is called as a minimal spanning tree. Now you understood the concept of minimal. The total number when you have a connected node and it is not a cyclic, then you can simply call it as a minimal spanning tree. Okay, is it minimal cost or minimal number of? No, it's the cost. Which is your cost. It's cost. Now, if I have a question, if we talk about minimal number of nodes, that is altogether a different scenario. Got it? Here, all nodes should be connected, so I cannot reduce the number of nodes. So, for example, let's take how many nodes are in this graph? How many nodes are in this graph? 8, right? When I'm designing a spanning tree, the 8 nodes should exist. All the 8 nodes should exist here. The V number cannot change. The V minus 1 should be the number of edges. So there can be 7 edges. So I'll just show you the total output for a minute. Just don't worry, I'm just going quickly to show you the last output. Sorry. And I went to other alone. Now, how many edges do you have? Just do the count of edges. You should technically get 7 edges. Got it? The formula. When you are converting a graph into MST, the number of nodes will not change, but the total number of edges that you will have will be V minus 1. So let's go to the algorithm that we use for this. Okay, in this session, we will not have a clear discussion about the algorithms, that how they are working or how they work, everything is there. There will be no pseudocode. Only topic that which I will not discuss in pseudocode is the Prince and Kruskal. Again, after this, we will work on various pseudocodes. This is a self-learned pseudocode because the Prince and Kruskal are very easy, but in this class, I will have some questions. Okay, first, okay, how many types of algorithms we can use? There are 2 types of algorithms. The one is called Prince and the second one is called as Kruskal. And these 2 algorithms work on a concept called greedy method approach. Do not worry if you doesn't know what is greedy method approach, but greedy is choosing the best solution to get an optimal solution. Got it. Now I have a question. You are standing at a node A. Okay, you want to travel from Hyderabad to Mumbai. Okay, that's a week. Assume that is a working day. And or it's okay. Let's not go with the working day example. Okay, working day example. At different times, you have different costs of the flight ticket. Which flight ticket would you choose? The cheapest flight ticket would you choose or the costlier one? If you have to travel from Hyderabad to Mumbai on a particular day, not even take working day or holiday, on a particular day, which one would you choose? Cheapest. Why are you choosing cheapest? Because it is, assume that it is the fastest and the cheapest route. Even not use the word cheapest for a moment, the fastest route. You will choose always fastest. In greedy, when we are working, we try to take an optimal solution, the minimal weight. Okay, you understood here greedy is taking the best route, best possible minimal cost route. Okay, that is fast and it is cost effective. You understood here the case of minimal when I use it is the better route. You should understand that. Okay, got it? Okay, have you understood that? If not, the understanding of this algorithm will become difficult. So first algorithm we will be working on the Prince algorithm. Can you see other algorithm name that I have written here, something called Dijkstra's algorithm? Are you able to see some algorithm over here? Yeah, this algorithm we will discuss next class. What is this algorithm is? As Vishwajit was asking, shortest route. See, this algorithm is an algorithm which is used to identify single source shortest path algorithm, and these are the algorithms which are used by mostly the Microsoft Google Maps or Apple Maps. So few of the algorithms, not all. Few of the algorithms, basic algorithms which they use is Dijkstra's algorithm. This we will discuss later. If you do not understand Dijkstra's, doesn't worry at all. Just we will focus on the Prince algorithm without knowing Dijkstra. Is that okay? Can I just go? Bishop total number of node traveled is equal to time and cost is 50. In case total number of nodes traveled is 5 and cost is 50. Which one we choose as MST? Great. Okay, Bishopjit has a very good question. So Bishopjit somehow had an example of a graph, and he says that there are total 10 nodes to be visited and the total cost is 50. And in his case too, he says there is only 5 nodes to be traveled and the cost is 50. Which one is MST? Basically, these are two different cases. In a graph, as I told you, all the nodes should be connected. So technically, if there are 10 nodes, all the 10 should exist. Got it? 10. You cannot say only I am reducing it to 5, then it is not at all a spanning tree. All the nodes to exist. Understood, Vishwajit? Since in your two cases, I cannot. But you can come up with these examples. You have got 10 nodes. In the first tree case, you are getting travel cost has to be 20, and in second case, your travel cost is going to be 30. So which one will you choose? Case 1 you will choose, because all 10 are existing and you are traveling with the minimal. Okay, let's quickly go. The first algorithm that we'll learn for the day is Dijkstra's algorithm. Okay. Now you can see this is it's a weighted undirected graph. Okay. Now see here it is already clearly mentioned that we are going to start from D. We are going to take the same example. We are starting from the D. Okay. Now the question is, you know the adjacents. You know your start point is also know that you are going to start from D and you are going to visit, or you are going to ensure that there is always all the vertices are connected. That can be directly connected edges or that could be an indirection connection. But each vertices is connected to some or other vertices, right? Now I am starting with D. Okay. Now what are the adjacent vertices of D? Just quickly answer this question. K stands for whether you have visited that vertices or no. The FF, it means that none of the nodes have been visited. The DV stands from the distance of the node to its adjacent node. You say DV, you're able to see what is DV. Okay. And next, I have something called PV, which stands for the parent of the vertices. Understood the three definitions: K, DV, PV. You understood? K is whether you have visited or not. DV is the distance to its adjacent vertices, and PV stands for the parent of the vertices, parent of the visited vertices. Now, I said D is my, and why all infinite I have written is. For instance, are these weights written or no? Are these weights written? Can you say there are weights written? Are the weight, is this a weighted graph or unweighted graph? But still, why? Wait, let me say. Okay, this weight is 2 here. This weight I missed. That's 2. You got it? That's E2. F2 is a weight. 2 is missing there. Okay, that value 2 I just missed here. I forgot to enter. So next slide it is entered. Okay, it's 2. Let me write it here so that no confusions. Okay, now let's, it's now, Anisha, it's correct for you, it's weighted, Now I have a question. I have written here all infinites. What it means? Now I have a question for you. If you answer that, you will be able to understand. How can I reach B from any node? Let's say, how can I reach from B starting from D? How will I reach? Guess, can you make a guess? I want to reach to B starting from D. How will I reach? D, E, B, D, F, B, D, C, B, multi answers I am getting, right? Multi answer. Which is the minimal? At instance, when you told me these answers, multi answers you got, but no one cared about minimal, or everyone cared about path. So to find out the minimal, B, C, D could be minimal, but we did brute force method. We did the brute force method. But instead, I say I doesn't know which path is minimal, but my solution will find always minimal. That's why I don't write the weights. Whichever weight I choose, the path I choose, that weight will be updated. Infinite is assuming a very larger value, because I have to find the smaller. That's why. You understand now why DV is written as infinite is. I don't know what is it path. If I find a path, that way I will update. Got it? You got it? Why dv is returned to infinite? So these values will get updated. So now, currently I don't know which will be the parent or which will be the parent vertices, because for D, if I choose to travel C from D to F, F to C, then the case is different. C's parent is F, not D. Got it? So that's why also parent vertices I have written. Currently it doesn't. Now what is our start vertices? Why K is F? Where K is F? Okay, KF means whether the vertices is visited or not. The K stands for visit or not. So just Boolean function here, the flag function, assume the flag is correctly false. Got it? Now let's start the algorithm. And once you understand prints, then only I'll go to cruise color. The start node is D. Okay, D. I have visited D. F. No, F is not vertices. So okay, very good question. This F is not vertices. Okay, this is a Boolean value. Boolean value, for instance. Okay. Now, since I consider D to be my start node, whenever I say D is my start node, I assume that is the parental node. There would be no more parent. So that's why I'm not updating. Now, why the value of D is written to be 0? That's first important. If I'm traveling from D to D, what will be the travel cost here? It is 0. Definitely, I'm not spending anything. If I'm standing at a location, the cost to reach to that location is 0. Assume that way. Is that clear? Why D is written T 0 and it doesn't have any parent? Clear that point here? What is meant to D? Okay, very good. The T means, yeah, I understand. The T here I have written simply saying that I have visited. This particular D node is to say that it is visited. True. You can say false is not visited, or true. Boolean values I told you, no. So 1, T stands for 1 and it is visited. Got it. Now, what are the adjacents of D? What are the adjacents of the D? Just say me the adjacents of D, for instance. It's a C, it's E, and it's F, and it's G. G is missing. Okay, great. Now, very good. One question. Now I can choose out of these all. Right. Okay. I have chosen. I have updated. From D, I can reach to all this. That is to C, that is to E, that is F to G. Got it? These are all I can reach. Yes or no? These all I can reach. Now, from D, which path would you suggest me to travel? These all are my paths. Which one would you suggest me to travel? Whether you suggest me to travel to C or G. Why G? Why G? Now say why G? Why not C? Bishajit said G is because of low cost. Because it is 2. It has got minimal. Someone says it is 2. Okay. Now I can travel from D to C, D to E, D to F, D to G. That's clear, right? Then you see, I say from D to C, I have to spend 3 rupees. No alphabetic order here. Just look at that. That's the problem here. To travel from D to C, I am going to spend 3 rupees. From D to E, I have spent 25. E to F 18. D to G, it's 2. In the greedy approach, I will always take the minimal cost. You got it? So what is the minimal cost here? G. I am going to choose G. Got it? So next I have decided from D to G I am going to travel. So D and G are connected. Now someone can say, let's be it a simple math. Technically, F and E is also minimal cost or no? F and E is also minimal cost or no? No, just for one thing. Is F and E is minimal cost or no? It has got cost 2. Is it minimal or no? No, just F and E's weight is 2, right? Even I will not choose this particular thing because in a Prince algorithm, it should be always connected nodes. See, D to G is connected. That's why I choose. Even F to E, no, I do not consider. So that's clear. So like something. Now where I have reached? I have reached to G. Now perfect. Now what next? What is the G's vertices? Can anyone say what are G's adjacent vertices? No, just say G's adjacent vertices. It is H and it is E. Just carefully observe here. D is already visited, so D will not. H, D, E, and D is visited, so H and E. Right, perfect. Now, what is the parent node of E in your table? What is the parent node of E in your table, for instance? In your table, okay. Does H as a parent node? Does H as a parent node? H has no parent. Okay. Now, so I have decided G. Now I wanted to update G's vertices, G's adjacent vertices. That is H and E. Have you observed anything at E point? Have you observed anything at E point? I have observed E's parent to be G and H parents to be G. Two things I did. One more important thing. Anirudh, parent change apart from that. Okay, let's go back one. Anything else? Now observe. E's parent is D, H we are going to add parent. What is the weight to reach E till now? What is the weight to reach E? dV value 25. dV value is from D to E value is 25. Okay, great. Just for one thing. After G node, what is the weight change? Here, can you observe here for instance? What did you observe? First, if you say, then we'll go to the next. Have you observed anything there? Have you understood what I am trying to do? Do not worry if you have not understood, but did you observe anything? Did anything got changed? Did you have no change? Just I am asking, did you find any change? Okay. Okay. You have seen this slide clearly? Okay. The slide clearly? Yeah. This slide you are saying there is some change. That is, one change is happening parent node and other change you are saying this particular value. Yes, 25%. Now 1 second. Just 1 minute. Just 1 second. Till now, how was the path connected? I said I am at D. I am choosing a minimal to travel. I reach it now to G. You just reach to G with the cost of 2. Now, if I have to reach E from D, I am spending 25. But G is connected to E and the cost to reach is 2. And from G I can go with 7. That's why I updated this particular value to be 7. You understood? Why did I change? Now I change it parent. To reach E, I have to visit G. Got it? When I am at D, you see backtrack it here. When you are at D, you can visit G. From G, you can visit D. Visit EE. Understood? No, that is total cost. If you put Kishore, you have very good question. If you write it as 9, then the problem goes to Dijkstra. The path cost, that is when we are talking about shortest path algorithm. That's why don't worry for the shortest. We are not working on path. We are just saying the weights of the edges. We will be choosing the minimal weights. You understood that or not? You understood that? Why if I write 9, it is going to be the path. If I write it as 7, it is going to be the weight of the edge. That is the only difference between Dijkstra's algorithm and the Prince algorithm. Okay. Okay. If path between D and E is less than 7, then E need not to be updated. Yes, very good question. Okay, someone had a very good question. Instead of this being 25, let's say instead of this being 25, let be 5. Then you don't do updation. Okay, see, I'm not using any tools Divya today so that I can scratch and immediately write. So that's why we had the writing skills, but for your happiness, I'll just do for instance. So let's say this value is 5. Okay, let's assume this value. In our next slide, there will be no update. Got it? So there will be no update. But unfortunately, our example we have taken 25, so it got an update. Okay, now what are connected? D is connected, G is connected directly. I know information about the edges of G and I know edges of I know the edges of D also. I know D's edges, I know G's edges. Now what next? I am at G. Now what next? Can anyone give me an answer? What next will I do? That's the correct. Vishal said either choose H or I can choose C. Anything you can choose, H or C. Okay, I am going to C because it's a PPT. I have already done C visit. Got it? Now I say I visit C. Minimum. Choose the minimum connected. Not E you will not choose. You will either choose only 3 out of 7. So which is the smallest path? You will choose the smallest path 3. Okay, so someone says, why H you can choose sharp. There is no, since I told I did this PPT area, I have chosen C here. Now if you want to choose H, perfectly correct, choose H. So what, there will be no updation, here H becomes true. Vishwajit, you have a correct answer. What you are trying to say is, I am at G, so that I will conveniently choose H. You are saying that is absolutely correct. But here you don't need to worry in which traversal you are finding. You will be only choosing D is there. D has got connections to G, C, E, and F. Whichever is connected, out of that I will be trying to take the smallest. For G, H is connected. So you are choosing this part. That is okay. Don't worry. So that is okay. Right? So if you say you have implemented with the stats or data structures with using other things, then things will come. Okay, got it? So you have the freedom to choose H of. Y for F, DV did not change to 3 as CF is minimum. Okay, with HB, I did not. From G, we need to move. No, we can move G to H or D to C. So I took D to C. Okay, next. Now, so I am at C. When I chose C, there was a change 3 to, that's it is visited. At C, now what is the minimum do I have? I have H. So I can choose this 3 or this 3. Till this point it is clear, or you have any questions just for a instant here? Because no, okay, no, okay, good. I understand, don't worry. Just one second, just one second. Very confusing, okay, don't worry. No, I did not have tools here, I am helpless. I am really sorry. Is this step clear for you? Is this step clear? Choosing of the start element and why we have written T, why we have written 0 and why we have written 1. Is that at least clear, or T is 0 and nothing? Is that clear? See, I understand. One by one we'll do. Once you understand, one will go. If not, we'll rework on it. Don't worry. So what I'm trying to say is, assume that you have a list in which you are saying that the nodes whose information is available. Now, what information do I have? I said I have visited D. I doesn't know what is the distance to reach to D because D is at the start. And from D, where all I can visit to C, I can visit to E, I can visit to F, I can visit to G. Is that correct? Can I visit from D to C, D to F, D to G, D to E? Right? This is what I can do. Yes. Now once I can visit, I said this is the possible visits I can do. From D I can reach to C, from D I can reach to E, from D I can reach to F, from D I can reach to G with the following cost. Is till this point it is clear? So is this clear till this point? Now let's move next. So I hope till this point everyone is. Now out of these weights, which is the minimal weight? Out of existing weight information, you have to choose the minimal. The 2, right? Now you say from D, I will choose the path to go to G. I will choose the path to go to G. Okay, you decided to. The moment you reach to G, you know G also is connected graph. G has certain edges, right? If you see G has also got some edges, yes or no? You see, G has got some edges. But we are not worried. Only we'll worry whether there is a path from D to G. Yes, there is a path from D to G where D is going to reach to G with minimal nodes. Till that point, just be comfort. Okay. After this, what is the next minimum that you can get in this particular list? Just in this list, what is the next minimum you are getting? C. Yes, that's why I am choosing the C path, but if you see here, I have done something also. The moment I reach to G, I have to update this list. I have to update the list. What are G's vertices? What are G's vertices? G's vertices is H. I have updated, and G's vertices E. I have updated the E's value with 25 to 7. Is this clear why I have updated 25 to 7? Now I say here that E cannot be reached from D. What I am saying, What I'm saying is, to reach E, I have to visit G. Divya, you have a very good question. So once this understand, my whole other topics become easy. So don't worry. Okay, very good question. 2 plus 7 is equal to 9. Very good question. Okay, very good. So before I start this, I'll have 3 questions. If you answer, then we'll go. Otherwise, we'll hold on and we'll work on those 3. What is path? Can anyone say what is the path which I can reach E with the minimal cost? Say me, what is the path from D to E? What is the minimal path? From D to E, what is the minimal path? DGF. Path you are understand. And what is the cost of the path? What is the cost of the path to reach E? Is 9. Perfect. Clear. What is the weight of the edge between D to E? What is the weight of the edge between D to E? No, D to E, weight of the edge, 25. Perfect, great. What is the weight of the edge G to E? What is the weight of the edge G to E, sir? Perfect, great. Now your question is, very good. Now your question is, why this 25 is not updated to 9, right? Is that your question? Why is the 25? Absolutely correct. Now I will show you. Here we are not capturing path. We are not capturing the path weights. What I'm capturing, I'm just capturing we are not capturing the total path. We are just capturing the weight of a path. You understood this? Do not get into cost or anything. We are just, okay, got it, I got it. D to E, you are saying it is taking 2. To reach E, I have to go to D to E, G to E, it is 7. If that is the case, then my algorithm is calling as shortest path algorithm. Here I am not working on shortest path. I am working on whether there is a connection or not, and this connection is minimum. So see, is the connection between E exist? How does the connection between E exist in this graph? First you try to say me that. How is the E connected in this graph? E is connected to B, E is connected to D, E is connected to G. But will you agree with that or no? First, will you agree with that or no? Say whether G is connected to D, G is connected, G is connected here. You agree. Now, what is the cost is to reach E, either I have to spend 25, yes, either I have to spend 10, either I have to spend 7, either I have to spend 2. Yes or no? Just say, what is the smallest cost available to reach E? What is the smallest cost available to reach E? 9 or 2? 7 or 2? Don't worry, the smallest cost involved to reach E. Do not even worry whether you are reaching from D, reaching from G. If I have to reach E, what is the smallest amount that I will spend? Just look at the graph. Just for instance, look at the graph. So you are still stuck at a particular point, so I have to go back once again. Okay. So just once you understand this, Prasanna has given me that. What are the E's in edge? What are the, okay. This all needs, that's why pen and stuff here. Okay. How many edges are incoming edges to E? To reach E, how many, through which edge I can reach E? 4. Perfect. From where all I can reach E? From which all vertices I can reach E? You are at E. Assume that you are standing at E. What are its neighboring edges? G, B, D, F. Everyone is missing F. Okay. These are the 4. Perfect. Now we are at E. What is the smallest cost that you can travel back? Is it 2 or is it 25 or is it 7 or is it 10? Which one is the cheapest cost? 2. Right? Got it? Now to reach E, I have to only spend from some node with 2. Got it? So that's why I'm working. If you are talking about this method of cost, I have to do lot of recursion. And my masters in minimal span, we do not use recursion. When you are using greedy, recursion concept doesn't come. Now for instance, you understand what is the shortest, that's why I did not use the word called shortest path. What I did is minimal spanning tree. To connect E node into my graph, I need only cost of 2. Got it? Okay, Lamba, you can just take time, because if you, let's take time in this case, right? Total time to reach is different. To reach E, if I am at F, I can just go with 2 rupees. Something like 2 minutes, something like this you can just. Is this word clear? First you understood the difference between path and weight of the edge. The sum of the edges is equal to path. Okay. Kalki, again you are coming back to this. See, weights, you just only write the weight of the edge. You are not going to write the weight or the cost of the path. See, do not get confused here. I understand now. Here your question is, instead of 7 here, you want me to write 9. Right or wrong? You want me to write 9. Correct? Is this what you wanted me to do? But problem is, if I do that, then it becomes the cost of the path. See, to reach E, I'm saying this is the only smallest route. I'm not. Who is I to say? The algorithm has to come. That's why instead of defining the total, I'm saying there is an edge which has got weight 7. That is what I'm writing. I'm just writing from G, there exists an edge with weight 7. That is what I'm writing. I don't know whether DGE is going to be path or not. So just I'm saying from G I can go to E or I can go to H, and this is the cost. From G to H cost is 7, G to E cost is 7, and G to H cost is 3. You got it? That's the difference you have understood. You understood what I'm trying to work on. Yeah. Both Divyas are saying no, and one said yes. So I think I'm going with a very pretty bad example. Okay, one thing we'll do here. We'll stop this session because I don't want to confuse you with too many things. So we'll stop the session for the day. I have 3 questions for you. Before coming to next session, just finish. Go through BFS and DFS clear. Is BFS and DFS is clear or not? BFS and DFS is clear. Okay. The word path is clear. Weight of edge is clear. The weight of everything is clear. Okay. See the difference between the path and the weight of edge in the next class. Yes, you are checking with the adjacency nodes here. Actually, what you are trying to do is, you are not going to update. You are just going to update. There is a path E. Instead of D being my parent, I will take G as parent, and it is 7. That is what you are saying. So here I am not using the word path. I am using the weight of edge. Once you get the clarity difference between path and weight of the edge, so I'll continue. If not, next class will work. Only at least sprints I'll finish here. Just 5 minutes I need. Okay, you understood why it is 7? Okay. Now the connected is DG and CH. What are nodes are connected? D and G. So I can choose which vertices. Say which vertices can I choose? So I have visited D, I have visited G. You understood that? D and G are visited. True. Now which vertices can I choose? I can choose vertices C, vertices E, vertices F, vertices H. No, I can choose all. I can choose either C, E, F, H, right? Which is the minimal? Minimal vertices batao. The weight with minimal. Only C and H. If you see the minimal, I have to choose either C or H. In this example, I have chosen C. Got it? C or H. Now I have chosen which one? The minimal. Now what is the update you have got C? I am saying I visited C, I visited D, I visited G, and what is the new vertices C? Do my table got any updation? Should I do what are the adjacent vertices of C? F, B, D, yes, correct, and B and D, right, it's B and F. Now if you see B and F, what is the weight to reach F? Till now I have, it is 18, and the parent is going D. Now I will change it to 3. Okay, see, 3 and parent to C. Got it? You understood this? Why it got? And B is the new edge. So we are going to update it to 4 and C because B is going to be the new edge and 4 and C. Got it now? Now which one will you choose? Which one will you choose? You can choose between F, you can choose between H, you can choose between C. Sorry, not C. You can choose between F and H. F and H you can choose any one. So I will be choosing F. F or H. Yeah, I will be choosing F. Okay. Now got it now to F. F is 2. What are the adjacents of F for instance? Say me what are the adjacents of F? It is B, it is A, it is E. Yeah, and D is visited. So just for instance, we will see non-visited adjacent. It's B, it's A, and it's E. Now from F to E, I can go. So see, now let me update that also. Let me update that also. From F to E, initially cost is 7. Got it? So A is 1, 10. Okay, from F to I can reach with 10. And you can see here any updation has happened. You see value F to F has got to, sorry, E has got to 2. Just see, E has got to 2. You got the difference? Now see, F is A and B and E. Why I am not updating B? Anyone can guess the answer? 3 edges I have. I have updated A. I have updated E with 2. Why I have not updated B? If you see B's parent is still E. Because B, the path if I choose 7 is greater, only the smallest, lesser. Have you understood the difference? You got it? What you have to do now? Okay. Now which one would you choose? Now which one? E will you choose or B will you choose? Now which one? Which one will you? Yes, perfect. And you will choose E. E's parents are already there, so no updation. Do we are doing any updation? Nothing. Next, which one will you choose? H you can choose. You got it? Your H got chosen here. If that was the reverse case, something C would have been chosen here. No issue. Now, what are the adjacents of H? It is A, it is B. Do we update A or do we update B? We will update A but not B because B has already, no, B's value is 4. See, B's value is 4, so I will not update. Only A is 10, so I will update. Okay, how did I selected H? Very good question. Okay, till this point it is clear. The one who had asked me the question, VC, you are clear till this? Yeah, okay. Now, which is the minimal path that is unvisited? H has got true, B has got true, or A has got these 3. Out of these 3, which one will you choose? H, B, or A? The minimal weight edge, sorry. Let me correct the word. The minimal weight edge, which is the minimal weight edge in A, B, and H? That's the reason why I have chosen H. The minimal weight edge is being chosen. Yes, because it has got the minimal weight. See here, you remember minimal weight. Okay, got it? So now I have chosen H. After H, I will update A. Instead of 10, it is becoming 4 and 4 A's parent is H. Now, which one will I choose? Which edge will I choose? You can choose either B or can I choose A? Anything you can choose. So let me choose A. Yeah, perfect. After that, it is finally B. Now, is this the minimal spanning tree? Remove all other edges. Here what I did is I have removed all other edges. Now all the vertices are connected or not? Are all the vertices connected or not? No, random here. I just said D is root node. You can start this example with B, you can start this example with C, anything. No, removing edge is not, okay, Sham, I did not remove these edges. What I did is the minimal path that I'm choosing to travel all through, this is this. Got it? So I just removed for easier understanding here. So this will be, if you select all these nodes, this is going to be your minimum spanning tree. You got, so if you do the cost to visit all nodes from one to other, totally with the longest being 21. The total cost that is involved to visit all is 21. Yes, there can be multiple MST, but cost will remain 21 only. Rudra, you have a very valid question. You will have multiple MSTs. For example, for example, let's take here. In this case, if you see the B's and A's both values to H, if you take this as case, see here, from H if you take A, or this value also got updated. So technically something, your path will change. So instead of this diagram, something else kept have come, but total cost will always remain 21. There can be multiple MSTs, but the cost will be always 21. Okay? Okay, one good thing I'll do with you. I'll not go to cruise curls. I'll just hold on for a minute here. Tomorrow, next class, that's not tomorrow. We have next Saturday again, we have got class. We will work on cruise curls. Before that, I'll have a problem. I just want you to give a small homework. If you have understood this concept, what was the root node that we choose here? What was the root node? D. Instead of choosing D as your root node, start with A as your root node and share me the problem. Okay, share me the solution for the same graph. Okay, for the same graph. Sorry, for the same graph, instead of D, choose the node A and start. See whether you will get the same output or not. By tomorrow evening, I'll share you some sample questions which you have to do and resubmit, which is not part of evaluation. Okay, forgot. This week, Friday, I'm going to release you the assignment here. Okay, is that should be okay for you guys? Submission date I'll extend and we'll work on it. Okay. Any other questions? Have you understood this concept? I know that if I had a pencil, it would have been very good. Rahul, I'll just confirm it on by tomorrow evening. Yeah, I have to just work on how to make group. If there is a province, I'll just work on. Okay, after Deepavali. Okay, correct. After the no submission dates, I'll extend. I'll just open. So you don't have class tomorrow here. Yeah. So just solve from A and share me the solution. If you have any questions, please do post. Otherwise, I'll start with the Kruskal's algorithm in the next class. Okay. Before that, I'll give you some homework. I'll see whether you are able to solve. Then we will go to Kruskal's. If not, we will try to work in some better way so that it is understood. Any feedback that you would want to share? I think one is